Welcome to this new season of the lecture series of the Network for Ocean Worlds. This network has been formed by NASA to advance comparative studies to characterize the Earth and other ocean worlds across their interiors, oceans, and cryospheres. In particular, the studies investigate their habitability, the search for biosignatures, and try to understand life in such environments.
And this is season 3 of this lecture series, and the focus has been on exploring ocean worlds through analogs in this year. And this is our last episode of this series, and we've been looking at different analogs, whether they were field analogs, laboratory analogs, modeling, and we tried to get a sort of a multi-thrust approach to one specific topic here. And we're very fortunate to have Dr. Elodie Gloesener and Dr. Angela Marusiak here to talk about some combined modeling and experimental approaches to clathrates. Okay, great. And so now we will kick it off with our first speaker, Dr. Elodie Gloesener. So Dr. Gloesener got her PhD in 2019 from UCL Belgium, and she was working on clathrates at that time, but with more of a Martian focus. And she's since come to JPL on a BAEF postdoctoral research fellowship, and is continuing to look at that work with this application to ocean worlds. And she's specifically going to be telling us about clathrates with relevance to Titan today. So Dr. Gloesener, please take it away.
Thank you. I'm going to share my slides. Okay, so can you see it?
Yeah. Yes, looking good.
Okay, thank you. So thank you so much for the invitation. I'm really glad to be here today to talk about the experiment that we do at JPL on clathrate hydrates, and especially the phase behavior in the presence of ammonia. So we started to study the interactions with ammonia to investigate the contribution of clathrates on the methane outgassing on Titan. And so I'm going to start with a brief overview of the Titan-based cycle, the methane-based cycle on Titan that is analog to the Earth water cycle. So in this cycle, you have a transport of methane from pole to pole on seasonal and orbital timescales. So polar and mid-latitudes will experience summer precipitations, while equatorial latitudes will experience periodic storms that may lead to short but intense fluvial activity on the surface. On the other hand, on geological timescales, methane will be destroyed in the upper atmosphere by photochemistry and charged particle chemistry, and this will produce heavier hydrocarbons and nitrogen-bearing species. And so these products that are liquid, like ethane, for example, will end up in the hydrologic system, and solid products will form the equatorial dunes. Regarding Titan's interior, it probably contains a large methane reservoir trapped in ice as clathrate hydrates. So clathrate hydrates are crystalline inclusion compounds that trap gas in cavity of hydrogen-bonded water molecules. So this methane reservoirs was either incorporated during the moon's formation or generated by low-temperature serpentinization reactions. So clathrate hydrates that contain methane as the main gas have been suggested as a dominant crystal material for Titan, and as clathrates have different properties such as thermal conductivity, so different from water ice, they may have played a significant role on Titan's thermal evolution, but you will have more information on that in the talk of Angela. So as I mentioned, methane is destroyed in the atmosphere of Titan, so in about a few tens of millions of years. And so there is a need to resupply this methane content to sustain the atmospheric, so the observed atmospheric concentrations. And so the clathrate are stable from the surface down to the bottom of the hydrosphere of Titan, and to destabilize them, to release the methane to the atmosphere, we need the occurrence of destabilizing events such as large-scale thermal events or impacts. So interactions with ammonia have been proposed also to dissociate or partially dissociate clathrates, and ammonia is a well-known clathrate inhibitor, and it is expected to be present in the icy crust of Titan. Another process that could release methane to the atmosphere is the substitution. So in this process, you have liquid ethane that would percolate through the crust and replace methane in the clathrate hydrates. So in our experiment at JPL, we focused to study the role of clathrate hydrates in the methane replenishment of Titan. And here I'm going to present you our results for the ammonia interactions. So first, we studied the phase behavior of THF clathrates with ammonia. So THF stands for tetrahydrofurane. It's a well-known clathrate former of structure 2, where THF molecules only occupy the large cages of the structure. And unlike methane clathrates that need high pressure to crystallize, THF clathrate can crystallize at atmospheric pressure at temperature lower than 277 Kelvin. And it makes it possible then to study the structure with a variety of different techniques. And THF clathrates also has similar properties to methane clathrates. And this is why we started to study the THF clathrates. So in the previous study at JPL, it has been found that a water THF ammonia system is very complex with multiple phase transitions. And you can see here on the left the phase diagram of the system. So it's with a system where THF is in excess. So the THF concentration is larger than the ideal molar ratio for THF clathrates. And what is important to note is that you can see the partial dissociation of THF clathrates with ammonia. So if you look at the red lines here, this is the dissociation temperature of THF clathrates, and you can see that it is similar to the eutectic, the liquidus of the water ammonia system. So the curve is almost the same, parallel to the liquidus. And so this first aspect of the phase behavior of clathrates is really important and has implication for Titan and outgassing of methane. And I will come back to that later in the presentation. The second aspect of the phase behavior of THF clathrates with ammonia is that in addition to the THF clathrates, upon further freezing of the solution, we will form another generation of THF clathrates that the stability limit is here. And upon further freezing, there is a third crystallization step that you can see here. And actually, it will form an unknown or new unknown phase that is assumed to be THF ammonia rich based on mass balance calculations. And here on the right, you can see the thermogram of the system with 13 weight% of ammonia. So that corresponds to the vertical line here on the phase diagram. And each endothermic peak corresponds to a phase transition. So for the peak here around 165 Kelvin, it corresponds to the melting of solid THF, because as I mentioned, we have THF in excess in the system, so that's normal that at cold temperature you have solid THF. The higher temperature peak here corresponds to the liquidus temperature of the first generation of THF clathrates that we will refer to as THF C1. The peak here around 225 Kelvin corresponds to the melting of the second generation of THF clathrates that we will refer to as THF C2. And the sharp peak that you see here just below 220 Kelvin corresponds to the melting of this new THF ammonia rich phase that we'll refer to as the low temperature phase. So here you have microscope images of the system at different temperature. So the top left image was taken at 163 Kelvin. So it's the temperature at which we saw the solid THF melting. So in this image, you have only 3 phases that are stable, both the clathrate phases and the low temperature phase. And when you are going to increase the temperature of the system, so the first phase that is going to melt is the low temperature phase. And you can see here at 223 Kelvin that it releases a liquid that is assumed to be THF ammonia rich. So when you continue to increase the temperature in the system, the next phase that is going to melt is the THFC2. And you can see there at 233 Kelvin that they are melting here just under a layer of THFC1. And when you continue to increase the temperature, so the partial dissociation of THFC1 is going to be initiated. And here on the bottom right picture at 253 Kelvin, you can see that they are in equilibrium with the liquid phase. So we investigated further these three different phases with Raman spectroscopy and X-ray diffraction experiment. And I'm going to present you that now. In previous Raman spectroscopy experiments, there were no characteristic features that could dissociate the THFC1 from the THFC2. And so we conducted additional experiments where our solution, so the water THF ammonia solution, was first atomized to ensure the homogeneity of a sample. And you can see an image, microscopic image here in the middle of our atomized solution. And so the microdroplets were directly deposited in a liquid nitrogen bath and then transferred with a pre-cooled spatula in the cryostage that you can see here under the laser of the Raman spectrometer. And so this is the typical setup of an experiment on the left, and the additional components are a temperature controller here and a door filled with liquid nitrogen that allows to cool down our sample. So if you look on the right here, you have example of Raman spectra we obtained in the stability regions of the THFC1 and the THFC2. And you can see that all the Raman spectra are similar. So they are all they exhibit all the signatures that are consistent with THF clathrates in aqueous solutions of ammonia. So you can see here the lattice modes at the lower wave number region and the OH stretching mode region here that exhibits the typical ice-like signature of water molecules in clathrates. The ring breathing mode of THF shows here a sharp peak that is typical also of THF entrapped in clathrate hydrates. So the absence of distinctive Raman features for THFC2 compared to THFC1 is in agreement with previous studies. And regarding the low temperature phase, so you can see at the bottom here, the kind of spectra we obtain in the stability region of this THF ammonia rich phase. And in addition to the THF clathrate spectrum that I've just described, we saw also additional signatures that are related to solid THF, including like the two sharp peak here in the ring breathing mode region. So for comparison, you have the spectrum of pure THF here. And apart from a strong fluorescence background, the Raman spectra didn't show any characteristic features that could be attributed to this novel phase. But nevertheless, we also observed fluorescence in a mixture of ammonia and THF here. And so this supports the hypothesis that this low temperature phase is formed by a mixture of THF and ammonia. So here on the left, you have our setup for our XRD experiments. So we prepared our samples by deposited our solutions, so the water THF ammonia solution, with a microsyringe into an open-ended capillary, and we sealed the capillary with a butane torch. The capillary was then mounted on the goniometer that you can see here, and its temperature was then lowered to 90 Kelvin via a liquid nitrogen cooled cryostream that you can see here under the goniometer. So the diffractometer operated in a 2 theta configuration that you can see here, where the X-ray source is stationary here on the left, and where the detector scans the range of 2 theta angles between 6 and 70 degrees. So on the right, you can see the examples of XRD patterns we obtain in the stability regions of the different phases we considered. So THFC1, THFC2, and the low temperature phase. And I will start by discussing the THFC1 and THFC2. So at 230 Kelvin, we have only one stable phase, so the first generation of THF clathrates, and the XRD pattern exhibit peak positions that are consistent with a clathrate of structure 2. At 220 Kelvin, here you can see that we have additional peaks compared to the pattern at 230 Kelvin, and these peaks are associated to the formation of THFC2, and they appear as additional peaks, but like at slightly higher d-spacing compared to the peak of THFC1, and it suggests then this THF clathrate follow also a structure 2. So when we look at the refined cell parameters, so here on the left, you can see so the evolution of the refined cell parameters with temperature. So the black lines are for THF clathrates, so without ammonia in the system. The blue lines are for the first generation of THF clathrates, and the red lines are for the second generation of THF clathrates. And the main thing to note here is that the THFC2 have a greater lattice parameter compared to the THFC1. So in order to look for or identify any structural differences between these THF clathrates, we performed Fourier difference analysis. And here on the right, top right, you can see a three-dimensional Fourier difference map projected with the clathrate host network. So for the THF clathrate control, so without ammonia in the system at 160 Kelvin here, and for THFC1 at 165 Kelvin here, you can see that we have only residual electron densities in the large gauges. So this structure can be said to form the conventional THF clathrates with THF molecules only occupying the large gauges of the structure. But when you look at the THFC2 here at 160 Kelvin, so you can see that you have residual electron densities in the large gauges, but also in the small gauges, and or around specific oxygen atoms of the water molecules network. So this results, in addition to the fact that the THFC2 have a greater lattice parameter compared to THFC1, it suggests that we have potential ammonia incorporation into the clathrate structure of the second generation of THF clathrates. So now regarding the XRD pattern of the low temperature phase, so you can see that we have additional peaks compared to the previous pattern that corresponds to the formation of this new phase. So here you have the poly refinement of our data at 90 Kelvin. So in addition to the reflection from the low temperature phase, we have also reflection from the S2 clathrates and solid THF. And so it makes the data as complex, and so it's kind of challenging to really fully solve the structure. But our refined unit cell suggests a trigonal symmetry for this THF ammonia rich phase with lattice parameters that are given here, so around 12 angstrom. So finally, regarding the water THF ammonia system, so here are some synchrotron XRD data collected at various temperatures for the water THF system on the left and the water THF ammonia system on the right with 11 weight% of ammonia. And so our samples were prepared exactly as the same way as I described before. And our measurements were undertaken at the Australian synchrotron facility. And you can see that the intensity of the THF peaks without ammonia in the system doesn't change at all with temperature. When you put ammonia in the system, the intensity will decrease progressively between 220 and 270 Kelvin. So XRD results show the partial dissociation of THF clathrates in aqueous solutions of ammonia, and it's in agreement with Raman spectroscopy and calorimetry data. So this is for THF clathrates at atmospheric pressure, but what about methane clathrates because I said like they need high pressure to form. And so we have just started a new experiment with a high pressure calorimeter that you can see here on the right. So the calorimeter is here, and you have like two high pressure cells that are deposited inside the cavities of the furnace. So the reference cell is kept empty during experiment, and the sample cell contains the considered solution, so either water or a mixture of water and ammonia. And the temperature control is via Peltier, and so we can have like the temperature, we can study the methane clathrates between minus 40 degrees Celsius, about 120 or 150 Kelvin, not Kelvin, Celsius, sorry. And so here on the right, you can see the high pressure piston compressor that is connected to the calorimeter, and it allows to the operation at constant pressure up to 400 bars. And so in our experiments, we use CH4 gas and constant pressure of 100 bar. And on the left, you can see some examples of thermograms that we obtained for methane clathrate hydrates formed with the multi-cycle method at 100 bars and with a heating ramp of 0.1 Kelvin per minute. So the blue thermogram corresponds to just the system with methane and water, and the orange thermogram corresponds to the system with 5 weight% of ammonia. And without ammonia, you can see that the onset temperature, so when the clathrate is going to destabilize, is around 286 Kelvin. So that corresponds to the expected dissociation temperature of methane clathrate at 100 bars. And when you look at the system with ammonia, you can see that the peak is broader than the endothermic peak without ammonia. So it indicates partial dissociation behavior, and also the liquidus temperature will be a little bit colder, like around 283 Kelvin. So that also shows the partial dissociation. So in the coming weeks, we will continue to acquire new data for the system with methane and with a different concentration of ammonia and with different pressure. So in addition, we also modeled the effect of ammonia. So in our thermodynamic model, it is based on the equalization of chemical potential of water in the hydrate phase and in the liquid or ice phase. So the chemical potential of water in the hydrate phase is given by statistical thermodynamics. So we used the Van der Waals and Plateau model, which is a well-known model for thermodynamic of clathrate hydrates. And so in this model, the chemical potential is given by, depends on the occupancy in clathrates, and the occupancy depends itself on the fugacity of the gas and the interaction potential between the gas and the water molecules of the cavity. So the fugacity can be given by an equation of state. So we use the Peng-Robinson equation of state. And for the interaction potential, we use the Gierach potential. So for the chemical potential of water in liquid phase or ice phase, it is given by classical thermodynamics. And for the water activity, without the presence of inhibitors, so salts or ammonia, we assume that the water activity is equal to 1 because the solubility of methane in liquid water is really small. And so here on the left, you can see the dissociated or the dissociation pressure of methane clathrate hydrate simulated with our model and compared to experimental data. And when ammonia is present in the system, so the water activity is going to change, and we express the activity coefficient of water in the liquid phase based on the Markos equation as proposed by Shukrun and Gazet 2010. And here on the right, you can see our results. So for the dissociation temperature of methane clathrate in the presence of ammonia at 50 and 100 bar, and comparison with experimental equilibrium data. So you can see that our model simulates the decrease of the dissociation point of methane clathrate with ammonia concentration. But the thing is that the Magus coefficients that I mentioned that have been derived for the water ammonia system. And so we will need more experimental data with in the ammonia water methane system to update those Magus coefficients. And so that's also the plan, to obtain more experimental data with the high pressure calorimeter. So as a summary, so we observed a new THF ammonia rich phase below 215 Kelvin with our XRD and calorimetry data, and our refined unit cell suggests a trigonal symmetry. Our XRD results show also the partial dissociation of THF clathrates in aqueous solution of ammonia. And so what does it mean for Titan? So the effect of ammonia on THF clathrate is similar to that on water ice. So that means that ammonia will interact mainly with the water molecules of the cavity rather than the guest. And the same behavior can be expected for Titan-relevant clathrate formers such as methane. And this hypothesis is even reinforced by recent experimental work from Clathrates and colleagues, where they show that ammonia has the same effect on THF clathrates, on cyclopentane clathrates and methane clathrates as on THF clathrates and water ice. So that means that on Titan, methane clathrates could be destabilized at temperature starting around 200 Kelvin. And this is a temperature that is expected to be within a few kilometers deep in the icy crust. So thank you for your attention, and I will be happy to answer your questions.
Thank you, Dr. Gloesener. Very nice talk. Sort through their questions. There's one or two questions up there already, so I will ask. Let's see. Sorry, 1 second. So let's see. The question is, does your work imply that methane clathrate will dissociate at lower temperatures in the presence of ammonia than without ammonia? And if so, how much ammonia is needed for this effect?
Oh, yeah, actually, we have already, like, as I show on the phase diagram, yeah, when you have ammonia in the system, so the temperature of dissociation of methane clathrate will be lower than without ammonia. So they will dissociate at colder temperature. And this shift in temperature depends on the concentration of ammonia in the system. So if you have more ammonia in the system, of course, the liquidus temperature will be much more colder than if you have like just 1 or 2 weight% in the system.
So sort of, I guess a somewhat follow-on is, could other molecules in methane, like ethane or ammonia, affect the formation and stability of clathrates on icy worlds?
Oh. If yeah, I didn't understand well. Like if ethane could.
Yeah, if ethane could affect the stability, is that?
Oh, ethane could affect. Yeah, yes. I'm like the stability of clathrates, so that it depends on also on the guest. So if you have like, for example, a mixed clathrates of methane and ethane, the stability will be different, or the same, the temperature, the dissociation temperature and the pressure, the dissociation pressure will be different for this clathrate than for just methane, simple methane clathrates. So yeah, if you have ethane in the clathrates, it will affect also the stability.
Okay, great. Thanks. All right, so we will please keep adding questions because hopefully we'll have a little time to come back to all of this at the end. But I want to keep moving. So thank you, Dr. Gloesener, again. And I would like to now introduce Dr. Marusiak, who is currently an assistant research professor at the University of Arizona. Dr. Marusiak got her PhD in 2020 from the University of Maryland, where she was studying geophysics and actually working with the InSight team and their instruments. And then she came to JPL as a postdoc and has continued on with both Mars and ocean world related geophysics. And so she's going to talk about how her current work it looks at the interaction of clathrates in these geophysical measurements. So Dr. Marusiak, please take it away.
Great, thank you. So I'm going to go ahead and share my PowerPoint. Yeah, so Elodie set me up perfectly to continue the discussion on clathrates and Titan. And as mentioned, I am a geophysicist by trade, so I'm going to be looking at how we might be able to detect these clathrates at depth and be able to figure out where exactly they are in Titan's ice shell. So as Elodie mentioned, Titan likely has a lot of methane clathrates that are contained in the upper ice shell. So because of Titan's size, it's possible that Titan not only has a surface ice shell, but could also have things like a high pressure ice existing beneath the subsurface ocean before reaching the silicate interior. And of particular interest is an upcoming mission, Dragonfly, which will be headed to Titan in the mid 2030s or so. And I'll talk about Dragonfly in a little bit, but sort of the key mission goals are to look at things like internal structure and composition of the ice shell, to be able to speak to how Titan evolved to its current state, and potentially answer questions about whether there's the ingredients needed to sustain our harbor life, either at the surface or in the subsurface ocean. Excuse me. So I focus mostly on methane clathrates because of the likelihood that they exist on Titan and its relevance to the Dragonfly mission. So from the Huygens mission, we know that Titan has a very thick methane-rich atmosphere. It's about 4% methane, with the other main constituent being nitrogen. So I love this figure by Mackenzie et al. And their PhD or Planetary Science Journal article from 2 years ago, where they sort of compare Earth to Titan, so you can see how much Titan does actually resemble Earth in a lot of ways. But one of the big questions we want to try to answer is, could methane clathrates be replenishing the atmosphere? And where are the clathrates in the ice shell, if that is where they're coming from? So through Dragonfly, one of the questions we want to answer is, how can we detect them at depth? So, we can go to the surface, we can do direct sampling, but that really only tells us, what is going on at the surface. If we want to look deeper into the interior, then we need to use geophysical methods to be able to figure out, what is going on at depth. So one of the things I just want to bring up is sort of the differences between a methane clathrate and a traditional water ice. So the bulk properties are actually pretty similar. Methane clathrates are much closer to ice than they are to something like, say, a granite or a basalt. But clathrates are slightly more dense, but really the big difference is they have a much lower thermal conductivity. And this will end up affecting how they insulate the ice shell and how they affect the thermal properties of Titan's ice shell. In terms of seismics, there are different dependencies on pressure and temperature for clathrates and for pure water ice. So one of the things I'm working on is how can we exploit that in order to be able to look at the seismic waveforms that Dragonfly might be able to record to see if we can use those to hunt for clathrates in the ice shell. So as I mentioned, that lower thermal conductivity, essentially what it's going to do is insulate the ice shell, and that's going to allow for warmer ice to exist closer to the surface. And this is not something that, my studies or the studies we did at JPL showed. This idea has been around for a while, and there was this really great paper that came out in 2020 by Kalasova and Soen, where they modeled different thicknesses of clathrate lids to see how it would change the conductive lid thicknesses. And I absolutely love this figure that they did. I use it a lot in my own work. And one of the somewhat surprising attributes is that the clathrates sort of have a maximum effect when they're 10 kilometers thick on top of the ice shell. So you can see in this plot here, the conductive lid thickness thins or has a has a minimum thickness when you have a 10-kilometer thick ice shell or a 10-kilometer thick clathrate lid. And then it starts to increase again as the clathrate lid thickness increases. In addition to just changing the conductive lid thickness, the temperature of the convecting ice will also change. So when you have pure water ice, it's significantly lower than as you add clathrates, and that convective temperature begins to warm. The overall heat flux is also going to change. It's going to drop as you add more clathrates in. And as I mentioned, sort of the maximum effect for conductive lid thickness is at 10 kilometers, but things like the heat flux and the temperature of the convective ice will continue to change as you add more clathrates. But for our study, we chose to focus on that 10-kilometer thick lid to sort of see the maximum effect that clathrates could create. Because if we can't see them at their biggest difference from pure water ice, then we're probably not be able to see them where their effects aren't quite as strong. So what does this sort of mean for Dragonfly moving forward? So it's a New Frontiers class mission. It's due to launch in 2027 and arrive to Titans in the mid-2030s. And among the instruments that it will include are DragMet, which among other things includes geophones and a short period seismometer. So the geophones are along the bottom skids of Dragonfly, and the short period seismometer will drop down from the belly of Dragonfly, get covered in a wind and thermal shield, and they will work together to record seismic signals. So the sort of big science goals that they want to do is measure things like composition, determine seismicity, so where, when, and why are seismic events occurring on Titan, and constrain the internal structure. So how thick is that ice shell? How thick is the clathrate lid or conductive lid thickness? Do you have high pressure ices beneath the ocean and the subsurface rock? So what I aim to do is look at how Dragonfly might or may not be able to determine if clathrates are present in that ice shell. And the way and the reason I want to focus on seismology in particular is because it allows you to see deeper down than just, the upper layers of the surface. And in particular, seismic waves are sensitive to a number of things, predominantly density of material, temperature, pressure, and then things like bulk and shear moduli. So clathrates in particular are going to have different densities, temperature, and pressure controls on things like seismic wave velocities, things like that. So previously, seismic waves have been able to recover like large-scale structure. So on Earth, we know, the crust, mantle, and core, and we've been able to do that for the Moon and Mars as well. But you can also investigate smaller discontinuities in the mantle and crust. So things like on Earth, we look at the mantle discontinuities, the 440, the 660 kilometer, also things like the D double prime layer at the core mantle boundary. We can do things like image subducting slabs and mantle plumes. So we can look for changes in temperature, which create slower or faster seismic velocities that we're able to pick up. And then we're also able to image the near surface. So the oil and gas industry uses seismology quite a bit and able to look for reservoirs and to be able to estimate, whether or not there are hydrocarbons of interest in the near surface. So we can do something, somewhat similar on Titan and search for our own hydrocarbons. But really the thing that I want to highlight is that seismic waves can really travel deep down through interiors where other investigations can't. So we can, partner with things like gravity measurements and radar. They all work very well together to be able to determine different boundary layers. But seismic waves are pretty unique in a way that they're able to go all the way down into the deepest parts of these planetary bodies. And that's why I want to see, can we use seismic waves to look for clathrates? And the way that I'm going to do this is using a open source model called Planet Profile. So it's available on GitHub. It's in MATLAB form. It's currently working on also being in Python. So you can go ahead and you can play around with it. It takes inputs like mass, radius, moment of inertia. You can estimate what you think the interior silicate is going to be. You can play around with ocean composition, whether you want it pure water ice or something akin to seawater, or have things like magnesium sulfates in there. And what we decided to do is play around with the surface ice composition. So we set up two end models. One is a pure water ice shell scenario, so it's 100 kilometers thick, and it's pure water in that ice shell. The other one is also 100 kilometers thick, but the upper 10 kilometers is pure methane clathrate. So you can see some of the differences here. So despite having sort of the same temperatures at the top layer and bottom layer, because of changes in heat flux and the temperature of the convective lid, or excuse me, the convection in the ice shell, they have different conductive thicknesses. So for the pure water ice scenario, the conductive lid thickness is over 30 kilometers thick, but when you add 10 kilometers of clathrates, you shrink that conductive lid thickness down to 11 kilometers, so about a third of the size, which is pretty significant. And as I mentioned, you also do change things like the temperature of the convective regime as well. So sort of to break it down in a couple different ways of looking at it, the overall pressure is about the same, because at the surface you have changes in density, and then as you go down in depth, they change a little bit, so the overall pressure basically stays the same. But what you may notice is in that first plot there, the temperature is really quite different. So that clathrate lid that's in the red, because the conductive lid thickness is so much smaller, warmer convecting ice is able to be much closer to the surface. And then if you look at the second plot there, we're looking at sound speeds and seismic velocity. So even at the surface, where they have the exact same pressure and temperature conditions, you can see that clathrate lid, or the clathrates, have a slightly slower seismic velocity, and that difference gets exacerbated as you go down in depth, and it maximizes right about 10 kilometers where the clathrate lid is. And then as the temperature and pressure profiles become more similar at depth, the seismic velocities are nearly identical. That last plot there is seismic quality factor, which we somewhat confusingly also use Q for, not to be confused with Q heat flux. What seismic quality factor is essentially how well does seismic energy propagate through material. So if you have a really high seismic quality factor, the inverse is attenuation, so you would have low attenuation. And that essentially means you keep a lot of the energy propagating. If you have a low seismic quality factor, you have high attenuation, you're losing a lot of energy. So the way that I kind of try to explain it is, think about jumping on a trampoline versus something like a Tempur-Pedic bed. You know, with the trampoline, you jump once and you're able to keep bouncing and moving. So that's an example where you have high seismic quality, low attenuation. With the Posturepedic bed, you jump on it and you don't keep moving. You just essentially come to a rest quite easily. And depending on how big your material is, you know, someone sitting a few feet away wouldn't even feel it. So that's an example where you have a low seismic quality factor, high attenuation. So when you look at this plot here, what you'll notice is that the clathrate lid goes from a relatively high seismic quality near the surface, but then very quickly drops down to a much lower value compared to water ice, which just has a bit more gradual decline from high to low quality factor. So to go back to that change in seismic velocity, one of the things we want to do is recover the seismic velocity structure of the ice. So we know, like from Earth and the Moon and Mars, you know, the seismic velocity alone can kind of tell you a little bit about what material you're moving in. So we wanted to look at that as a first stop of, okay, can seismic velocity alone be different enough for us to say that you're traveling through ice or you're traveling through clathrates? And it turns out that you do get quite a big difference. At maximum, it's about a difference of almost 9%, which is pretty big. So to give you an idea, on Earth, we know seismic velocities down to, you know, up to 1 to 2% uncertainty. So very well. However, the caveat there is we have a lot of seismic stations, and we also have a lot of seismic sources, aka earthquakes. Now for Titan, we're going to have a single station. It is allowed to pick up and move and fly around, but at any given point, you have one seismic record. And you know, we're not 100% sure how much seismicity Titan is going to give us until we go there. But we know, you know, from tidal estimates, it's, you know, not going to be quite as high as a body like Earth that has plate tectonics. So it's, you know, that 9% while big by Earth standards, is not something that's, you know, the silver bullet. Yeah, we'll definitely be able to see a difference in 9% seismic velocity on Titan. We could, you know, depending on the number of events we get and their quality and where they come from. It's, you know, I'm not saying that we're not going to get uncertainties that low. I'm just saying we may not be able to get uncertainties down to the level where we can point to clathrate versus ice. But you know, there's some other tools that we might be able to use. So since I doubt anyone or most people here are seismologists, just as a brief overview, in terms of seismology, there's sort of two seismic waves that we talk about. Body waves, so those are things like your P, your S waves, and then surface waves, which are things like your Love, your Raleigh wave. In ice, you can have Crary waves as well. So body waves will travel through a body in the interior, and surface waves will travel along the surface of the body, along the exterior. So with body waves, because they dive down into the interior of the planetary body, they tend to be more sensitive to seismic velocities at depth. But since surface waves only go along the surface, they're very sensitive to what's happening in that upper layer. So while body waves, you know, maybe won't help us out too much if clathrates are only near the surface, those surface waves are going to be particularly sensitive to those changes between the clathrates and the water ice. So we can see that if we look at hypothetical seismograms. So this uses AXISA, which is a HPC, so high performance computing cluster software that's open source. So we fed it our two models to see, okay, what do we think those seismic records could look like if we have different size events? So these do not have any background noise in them. That's why they're so clean, but it allows us to directly compare water ice to clathrates. So the shaded gray regions of those three diagrams are where the surface waves are occurring. So in that upper plot there, you'll notice like the first arriving P, S waves, surface waves, they're all very close to one another. And it's kind of hard to distinguish the difference between pure water ice and clathrates. If you have really good eyesight, you might notice that clathrates arrive just a smidge sooner than the, the pure ice arrives just a smidge sooner than the clathrates because they travel a little bit faster than the clathrates do. But then when you go out to a distance of, say, 50 degrees, in that shaded region, that blue signal is significantly higher than that red signal there. And that's because the pure water ice is traveling through high quality or high seismic quality material. So it's able to maintain a lot of its initial energy. But clathrates are losing a lot of that energy, so their amplitudes are being diminished. And same thing happens again when you look at, you know, even an event from much further away, essentially on the other side of Titan. You can't even really see the clathrate signal compared to the pure water ice. So another way to sort of quantify that is to look at a root mean square. So essentially I take each of those seismograms and I come up with a single value that's representative of sort of, not quite the average, but the amplitude that you will. So I can directly compare what is the ratio of pure water ice to clathrates. So if they had the same amplitudes, that value would be 1. However, they don't. So at short distances, clathrates actually do have a slightly higher amplitude than do pure water ices. But once you get past 10, 15 degrees, that rapidly changes. And once you get out to about, 75, 80 degrees, pure water ice will have 10 times the ground motion that a clathrate lid would have. And that all comes back to that seismic quality factor. So you have clathrates, which are reducing the conductive lid. So you're allowing higher temperatures to exist closer to the surface. That higher temperature is going to reduce your seismic quality factor, which means you're going to be dampening the surface waves. So clathrates are going to have a reduced amplitude compared to pure water ice. So there are some other considerations that have to be made. So I don't want to say that, directly looking at the amplitude ratios is going to be the silver bullet for Dragonfly to say, yes, we have clathrates, because there are things like the depth of the seismic event that could alter the seismic velocity. So if you have a deeper event, you're not going to be producing a lot of surface waves. If you also have high porosity, you're going to be creating scattering effects. that can also reduce or otherwise affect the appearance of surface waves. So this is a big problem when we have seismometers on the moon, is that these scattering effects made it a little bit difficult to interpret the Apollo seismograms, but hopefully seismometers will be heading back to the moon and we'll be able to mitigate some of those effects. There is the possibility that other organics or other materials could resemble clathrate properties. So there's a student who works at JPL, Andrea Bryan. This is one of the things she's going to potentially be looking into, is what other things could mimic clathrates. And then, in this modeling scenario, we either said it's pure ice or it's pure clathrate, and there's a hard boundary between them. That's probably not going to be the case for Titan. You're going to have some mixture of, 80% clathrate, 20% pure water. There's going to be probably not a hard deadline, but more of a, gradual change from water to clathrates. We don't exactly know. So that's going to complicate things a little bit. But sort of what I want to highlight is that clathrates are definitely going to be insulating Titan, so they're going to be causing changes in the thermal and seismic profile compared to if you had that pure water ice. So as we get data back from Dragonfly, if we start to see that the conductive lid is, thinner than we would anticipate, that can sort of point to, yes, clathrates are present. And if we can get really high quality seismic events where we can constrain with low uncertainty the seismic velocity structure, that can be one great tool to point to how deep are the clathrates. So seismology can definitely help determine how thick is that clathrate lid, where are clathrates present in Titan's ice shell. But I do want to highlight that they are just one tool in a plethora of toolboxes that we can use to go and explore clathrates at Titan and hopefully other bodies as well. So with that, I'm happy to take any questions that you may have.
Thank you, Angela. That was a wonderful presentation as well. Really interesting. And we have some questions coming in here. So give me a second. So how would the different types or structures of clathrates that were sort of, seen in Elodie's presentation affect the thermal effects that you're talking about? Have you been able to look at, what different clathrates do?
It's one of the things that we've thought about. So really the big thing that changes between pure water ice and the clathrate lid is the thermal conductivity. So if the different structures of clathrates have different thermal conductivities, then we might be able to kind of look and investigate how much they may differ. But from sort of the preliminary stuff that we looked at, the differences weren't as great among the clathrates compared to pure water ices. In order to integrate it in our program, we also do need to make sure that there is data available for, the seismic velocities of clathrates as well. So that's an additional area of research where we're trying to expand. Is could we do mixtures of ice and clathrates to be able to see, what the seismic velocity of those different concentrations are, so that we can better integrate it in our model.
And so another one is, what would a non-detection of clathrates by Dragonfly imply for methane or the ice layer? Or what kind of, limits can you place on things?
Yeah, I don't know if we would truly be able to say definitively clathrates aren't present at all. I think that would be really, really surprising if that did come back. So in that scenario, we would get seismic velocities that were very close to water ice, or, we could be able to say, this is the change that we're seeing is from porosity or from these other sort of things that we're measuring. But in terms of what that would mean for Titan, that would have some pretty big implications. It would kind of mean we'd have to rethink how is the methane getting replenished in the atmosphere? What does that mean for sort of the cryovolcanism that we're seeing? So yeah, I would be very shocked if we had a definitive non-detection.
Okay. And I guess a question maybe for both of you, where do we expect clathrates to exist elsewhere in the solar system? And, what kind of, are there other sort of molecules they could be hosting, other kind of exotic systems that people are thinking about?
Sure. So I can speak for me. I mean, we do have clathrates here on Earth. the oil and gas industry has actually studied them quite well. The other body that I have thought of is Europa. So Europa probably wouldn't have methane clathrates. It would probably have oxygen, carbon monoxide or dioxide, potentially sulfur. And they may not actually be present at the surface as much as, throughout the ice shell closer to the ocean. So I think it's definitely intriguing to think about, where else could we see clathrates, and I'm always a big fan of let's stick seismometers everywhere. So I'm happy to get seismic data and look at whether or not they are present at other bodies in the solar system.
Yeah, also like carbon dioxide clathrates have been suggested to form also on Mars, so in the polar caps and in the subsurface. And yeah, there are some, I actually like when you have like the good high pressure and low temperature conditions and water or ice with a gas that form clathrates, and there are a lot of gas that can form clathrates. Yeah, you will have clathrates, and so yeah, you can have like in icy satellites, also in the solar system.
Great. One other question. What range of ammonia is expected to potentially be present on Titan in the water ice there? How much is that going to be a factor?
Oh, I think it's not so much. It's like a 1 or 2% weight percent, but so it won't allow like so the dissociation temperature of methane clathrate then will be decrease of a few degrees with this weight percent, but you can have already partial dissociation. So the partial dissociation will start at the eutectic, and so you won't have like total dissociation of methane clathrate, but even like with a few weight percent of ammonia, you can have partial dissociation.
Okay, thank you. And we are just about at the hour, and so want to be respectful of people's time, but I want to thank you both again for really excellent presentations and a really interesting discussion. Thank you all for joining, and you can check things out on YouTube, and we'll be announcing the new series soon, so please join us again. Bye-bye all.
Thanks for having us.
Yeah, thank you.